Hello, everybody. Are we in weird times or what? So here's the plan. I am going to break these lessons into little pieces so that you don't have some giant hour and a half long video to watch. So you can watch it in little pieces. So what I'm going to do is go through just section 6.1, just talking about the notes and definitions and things like that. And then I'm going to put another video that'll have a bunch of examples on it. And you're welcome to work through as many examples as you want, or just not even worry about it if you think you've got it. Okay? So this is just going to be the notes portion where we just kind of lay down some definitions and look at my creepy hands, and that'll be fun. And then we'll bust out calculators here in a minute on the second one. Alright, so we're going to get started here. We're going to try to roll through chapter 6 this week. We're a little behind now, and for some reason they're not throwing anything out. So we'll see if that changes or not by the end of the semester. Alright, chapter 5, the one that you just finished, that you were working on over the break, was about binomial distributions. And we had this formula that we came up with, and we said we're going to have n objects, and we're going to choose x of them to put in the group. And then we had p was the probability of a success and x successes, and q was the probability of a failure, and n minus x was the number of failures. And so it was easy to say, okay, if 9% of men are colorblind, and I have 6 men standing here, what's the probability that 2 are colorblind? It was easy to go and find 6 choose 2, 9% to the 2, 91% to the 4, and we could just figure out what the probability was. Alright, so that's really nice and all, but that's not how it always works. So a normal probability distribution, which is all chapter 6 is talking about, they're all normal distributions. There's not a success or failure, there is a continuous distribution. And so think about a full curve where everything is connected together instead of success or failure. Alright, so remember normal distribution looks like a bell-shaped curve. Like I said, it's for continuous data, so I can't make a table of values like we could before. I can't say the probability of 1, the probability of 2. It doesn't work that way. So we don't make a table of values. Everything in here is based off of mu and sigma, and I'm sorry that's kind of fuzzy. At least it looks fuzzy on my screen right now. This camera does not seem to like this font. Alright, mu and sigma are going to define everything. Remember, mu means the mean, that's in the middle, and sigma is the standard deviation. And so when I go this direction, this is 1 standard deviation, this is 2 standard deviations, and this is going and subtracting the standard deviations, so minus 1 sigma and mu minus 2 sigma. Okay? And that divides up my bell curve into different standard deviations. Remember that the total percentage under here is 100%, and 100% written as a decimal is 1. So the area underneath this curve is 1. The area underneath the curve is 1. It's 100% of all the probabilities put together. The x-axis also, if you'll recall, is a horizontal asymptote, which means this isn't really touching, it's not really stopping here, it's continuing on, it's an asymptote. Okay? So, we have talked about these normal curves before. We talked about all of the percentages and we broke them all down for 1, 2, and 3 standard deviations away. But we're going to dive a little deeper into that, okay? Alright, next, let me show you what's going to happen here, a little notation. instead of having the probabilities in a table, these are continuous, which means I could just take this little slice of this here, 1.4 standard deviations away, and that little slice would be a probability. Okay, so all the probabilities together is the area under the curve. So we're not going to find the probability that we pick 2 colorblind men out of 6. What we're going to do is find a probability that is less than or greater than 2, for instance. Okay? Now, did you notice that this one says or equal to and this one does not? Here's the thing. It does not matter. It doesn't matter. We're not going to worry about whether it's equal to or not with this because it's continuous distribution, not discrete, where it's just jumping. Okay? So continuous. So, when I say the probability that x, this is our distribution, is less than or equal to x, our value, what that means is, well, if this is my x value, my little x, the probability that it is less than that is everything over here. It's this area. Okay? When I say the probability that this thing is greater than x, this event, there's my x, and it's everything up here. Okay? Now, again, does not matter if it's equal to or not equal to. Doesn't matter. What matters is whether it's less than or greater than. It matters which side of x we're looking at. Ooh, sorry if I broke your eardrums. Okay. Here's the formula for finding the area of a particular slice. But there's so many slices that we could use. There's an infinite number of them. So this is way too clunky for general use. So we change these normal distributions into something we call standard normal. And we'll have a table for that. So I'm going to explain that here in just a second. If I wanted to find the probability of x is less than or x is greater than, sorry, boy, I started talking and it choking me up. Alright, so we would have to use calculus, because calculus finds the area under a curve. That's what calculus is. It finds areas under a curve. Okay? So, long story short, we are not going to be plugging this into our calculator. Hooray! Instead, on your little happy orange sheet, this guy, there are tables in there, and we're going to use those tables to do some of this happy work. Okay? Somebody already did the calculus and they recorded all of that stuff. Alright, so what we are doing is finding the area under the curve, either to the left or to the right of a particular value that we want to investigate. Okay? Here's the problem. Since it's all based on mu and sigma would change with every single situation, it's not good to use. So what we're going to do instead is to change it to something we call the standard normal distribution. It standardizes it. So, instead of this whole situation with, sorry about that, mu plus sigma, mu plus 2 sigma, mu minus sigma, mu minus 2 sigma. Okay? Instead of this situation, we're going to change mu to be 0. And we're going to standardize it by changing sigma to be 1. So when I add 1, or I add 2, or I subtract 1, or subtract 2, this is the number of standard deviations from the mean. This is found, we use this using the z-score. Remember that guy? We haven't talked about the z-score in quite a while. I think that was chapter 4. So, the z-score is going to take the old mu and sigma from our data, and it's going to turn it into a number of standard deviations away from the mean. And so this standardizes all of the work to be the same so that we can use the same tables for all problems, no matter what their mu and sigma are, because z is going to do all the work for us. So this guy is super important. Z is x minus mu over sigma. Always. It's nice. It's a beautiful thing. Okay? So we're going to take our problems and we're going to change from an x value with a mu and a sigma into a z-score, which shows number of standard deviations from the mean. And this z-score, because it's standardizing the data, is called the standard score. So I just call it the z-score because z-score is a nice easy way to remember it, because that's what you're finding. Your book will sometimes say find the standard score. That's z-score. Z standardizes. Okay? So that's the big important thing you need to understand, is that we're going to change from a specific mu and sigma from your data, a mean and standard deviation found from your data, turn it into z's, which are just numbers of standard deviations from the mean. So we call the mean 0 so we can go with number of standard deviations away. This is a lot easier when I can see your little faces. Alright, next. We would like to also have another version of this formula for use. What I'd like to do is to solve this equation for x. Woohoo! We're going to solve for x, and we're going to have another form of the equation that will be useful to us later on in the chapter, okay? So to solve for x, first thing you would do is multiply by sigma. Alright, sigma for each. So I've got sigma z, and then sigma cancels. I have x minus mu. To continue solving for x, I add mu. So I have sigma z plus mu equals x. This is a second form of this formula for z that we will use later, and he'll be really handy. So go to your orange sheet, chapter 6. Z-score is also called standard score. Okay, and we're also going to have z sigma plus mu, which I wrote it in the reverse direction. It doesn't matter. Okay, so these two are going to help us find some nice probabilities. Alright, I'm going to put some examples in another video so that you can go back and look at them and stop and pause and practice and that kind of thing. And it'll keep the videos a little shorter. Alright guys, good luck.